Okay, problem number 4. We've seen this problem often enough, and this type of problem. You should be able to do this one in your sleep, but I'm going to ask you to stay awake during completion of this problem anyways. Let's get started with 4, part A. It says the rate of change of a function y with respect to time t is proportional to the function y. Part A says write a differential equation to model this situation. So the rate of change of y with respect to t is written as dy dt. We're proportional to y, that means equals k times y. And that's it for part A. Now in part B, we're supposed to solve this differential equation. So let's separate the variables. Divide both sides by y and multiply both sides by dt. And there you go. Separated the variables. We get all the y's on one side, everything else on the other. Remember, we know to solve for y because this is the derivative of y with respect to t. So y was the function that was differentiated. Y is the function we're going to solve for. So now, let's integrate the left side and integrate the right side. The integral of dy over y is natural log of the absolute value of y plus a constant. The derivative of k with respect to t. Remember, k is a constant. That's kt plus a second constant. Now what we want to do is subtract constant 1 from both sides. Constant 2 minus constant 1 makes a different constant, so we'll call it c sub 3. And moving on. We want to get y by itself. So how do you get y? How do you get a variable out of a natural log? How do you get the variable out of the input of a logarithm function? Well, use an exponential function. This is going to be e to the kt plus c3 power equals the absolute value of y. Now we're getting closer. E to the kt plus c3 can be rewritten as e to the kt times e to the c3. Okay, now moving on. Let's continue. E to a constant power is another constant, so we'll call that c sub 4. Let's pull that constant out in front. C sub 4 times e to the kt power equals the absolute value of y. Then you get rid of absolute value bars by taking plus or minus of the other side. Now right now, we're in a situation where plus or minus an arbitrary constant times e to the kt power. Well, plus or minus a constant that could be positive or negative. It's kind of redundant. So the plus or minus signs are okay to write, but they're not necessary at this point. So we can say c times e to the kt equals y. And there you go. This is our exponential growth and decay model. Now let's move on to part C. In part C, we're supposed to prove Vleck's theorem. Vleck's theorem talks about the constant of proportionality in half-life problems. So let's start with our exponential growth and decay model. Y equals c times e to the k times t power. And now let's solve for k. Divide both sides by c. Now remember, y represents the ending value, and c represents the starting value. Well, if you're talking about half-life problems, the ending value is going to be half of the starting value after the set time. You know, t is the half-life in years. So we can say that y over c, that's going to equal 1/2 for these half-life problems. So now we can say 1/2 equals e to the k times t power. Now, I want to solve for k. How do you get a variable out of the exponent in an exponential function? Well, we use a logarithm. It's log base e. So, log base e is what we call the natural log. The natural log of 1/2 equals k times t power. Now we'll solve for k by dividing by t. And here you go. The constant of proportionality is equal to the natural log of 1/2 divided by t, where t is the half-life in years. And that's a proof of flex theorem. All right, thanks for watching this video. Hopefully this was helpful. Good luck with the next problem.